All right, so as we continue work on acids, bases here, this is naming acids. So you're not going to find this dealt too much in your Glencoe text, but still need to know how to do this. So follow along with your notes, and I've highlighted the blanks for you, so we'll kind of focus on those. But naming binary acids. Okay, so binary means two. Bi is two. So binary acids would be acids that have two elements. Obviously, one of them is going to be hydrogen. Acids release hydrogens or donate hydrogens to the water molecules in solution, so we need to have a hydrogen. So when there's just binary, just two, the name always starts with hydro. Okay, so hydro, the H is hydro, and it's at the beginning. Now the stem of the word itself is from the anion. Okay, the anion is, stem is from the anion. The anion here should be bolded. That's part of your notes there, not the stem really. So the anion is the negative ion. So obviously H is the positive ion and fluorine is the negative ion. So when that produces HF, the name of this would be hydro, and then the stem comes from the name of the anion. So fluor, fluorine, the stem is fluor. Okay. And then the ending, the suffix is ic. So we've got hydro, stem, ic, hydro, fluor, ic. You'll see here we have hydrochlor, ic. And then acid is at the end. Acid is at the end. You name the acid there. When we have HI, hydro, iodine, iodic, hydroiodic acid. So that's pretty basic. Hydrobromic acid would be another one. That's pretty basic. Ternary acids and bases. So ternary is when we have three elements involved or more. Ternary specifically we'll be dealing with most of our examples. Here we'll clearly identify three different elements. So when three elements are involved in the acid, the naming is just a little bit different. It's a little bit more complicated in a sense. Generally the most common form of the acid, and because there's more elements involved, you could actually have different numbers of hydrogens, different numbers of oxygens, and things like that. So the naming has partly to do with the different variations of the same three elements. So generally the most common form of an acid is given the suffix ic. And we'll just have to go through to so that you can identify some common acids. We'll get to that. But H2SO4 is this is the most common kind of version with H, S, and O in an acid. And so it is called sulfuric acid. The stem comes from the element that's not an H or an O. So this is chloric acid. So there's no hydro at the beginning. If it's ternary, just focus on the stem. So common names generally come from the element that is not the H or the O there, as I mentioned. Okay. Now here's where it gets a little bit tricky, and again, it's just becoming more familiar with what's the most common and what's not. And again, if you memorize your acids on the acid table, you'll see how these naming principles follow the ones that you memorize. But generally, if the acid is formed with one fewer oxygen than the most common one, then the suffix changes to us, from ic to us, O-U-S. So, for example, if we have H2SO3 with a little minus there, H2SO3 minus, well, that's sulfurous acid. Okay, sulfurous. And this actual type of naming is common in other areas of chemistry too. These are a little bit older styles of naming with the ic and the us, but I think I mentioned in the lab the other day that, because you had ferrous sulfate, right? Remember that was a chemical we used in a lab, ferrous sulfate. So that talks about the ion that is the lesser charge. The ic is the ion with the greater charge. So when you have one fewer oxygen, you can remember that it's us. So sulfurous acid. If the form has one more oxygen than the common form, the suffix is still ic, but there is added a prefix that is per, P-E-R. So HClO3 would be, right up here, chloric acid. You see that? Chloric acid. So if we had HClO4 as an acid, that's perchloric acid, with the per at the beginning. Perchloric. Now if we go the other way again, and if the form has 2 fewer oxygens, and I think this is probably as far as we're going to go in all these different naming strategies. If it has 2 fewer oxygens, then the common form, the prefix is hypo, and the suffix is us. So again, going with the H, the Cl, and the O, okay, if we have 2 fewer oxygens, HClO, it's hypochlorous acid. So you're going to want to study these rules. You're going to want to study your common forms of the acids, and that's probably as far as looks like as far as we're going to go here with the naming. That's going to get you quite far. So you can refer to those rules when coming across acids in labs or in your textbook. Okay. So obviously the ternary acids and bases are a little bit more complicated, but as you read through the textbook, you'll get familiar with that. Okay, so that's all it is for naming here that I'm going to talk about. There's just a few other things that I want to throw in here. So net ionic equations. Now, I believe we've talked about net ionic equations before, but there is going to be some more mention of them. And just so we're all on the same page, for a net ionic equation, it's the final chemical equation where all spectator ions have been removed. So, okay, first of all, net. If you have gross income versus net income, the net income is what you actually take home. The gross income is what you actually technically make. But when you take away all of your taxes and your payments and stuff, what you're left with at the end is the net. So think about a net ionic equation. It's what ions are all left over when everything else has been sort of omitted that's not involved in the equation. And the ions that are omitted, that are not involved in the equation, are called spectator ions. And that makes sense because if you're going to a game, there are players and there are spectators. The players would be the ions that are actually involved in the game, and the spectators would be the fans that are just kind of sitting there watching, or just kind of, they brought the players to the game or whatever, right? So the spectator ions kind of bring the players to the equation. So let's do a little example. I guess I should highlight here these two. Represents only ions taking part in forming the compound that is generally insoluble. So an example might be this. If you have sodium chloride plus, let me just quickly take a look. Was it calcium nitrate? Okay, was my example. Calcium nitrate. And we're going to have to write that properly. Of course, 2 nitrates for 1 calcium. Now that's going to produce, let's pretend this is a double replacement, right? So we're going to have NaNO3, and we're going to have CaCl2. Okay, so we're going to have to balance this a little bit. What do we need to do here? Okay, I think is that good now? 2 NO3s, 2 NAs. Okay, so in reality here, if we look at these compounds, NaCl is very soluble. So this is actually, and I'm sorry, you don't have a lot of room on your paper for this. I didn't leave you space. You write this wherever you can find space. But this is sodium chloride soluble. So we actually have this in solution, right? We actually have these ions that are floating around. This is not a solid. When you put it in solution, it's not a solid, right? We also have a calcium 2+ ion, and we have 2 nitrate ions. Right? Over here, now sodium nitrate. Do you remember if that's soluble or insoluble? Anybody remember from our solubility unit we just went through? Soluble or insoluble? Guesses? There's a double whammy here. This is pretty obvious. Insoluble? Soluble. Close. Soluble. Yeah. Okay. Yeah. Okay. So sodium, right? That's the first column. Okay, so generally all those compounds with sodium are soluble with anything from the first column. Nitrate, okay, nitrates are also soluble. There's very little exception, very little conditions that would make this insoluble. So this is from here and here, from looking at both those ions, definitely soluble. So 2Na plus 2NO3 minus, right? Now CaCl2, that's going to be insoluble. That's going to be only slightly soluble. So guess what? We actually have CaCl2, and we're going to say that's going to form a solid in these conditions at this temperature and all that. So net ionic equations, again, what you want to do is you want to realize, hey, what is soluble, what is in ionic form, and what is insoluble and probably in solid form. And then you're going to start to piece away. So look at these sodium ions here. They really do not take part in this equation. There's sodium ions at the beginning, sodium ions after the reaction. They just bring the chloride ions to the game, you see, and then they just sit and watch. Calcium, okay, that's going to be involved in the actual reaction. But nitrate, look at this, nitrate here, nitrate here. So these are all spectator ions that are really not involved in the reaction. The net ionic equation then is going to be your Ca2 plus 2 Cl minus produces CaCl2. And this is going to be solid. These are going to be aqueous. Don't put liquid. They're aqueous, they're dissolved in water. So that's your net ionic equation, okay? And that's going to hold true for your acids and bases here too when we write equations. Acids are going to fully dissolve, bases are going to fully dissolve or dissociate, and you're going to have a lot of spectator ions floating around in solution. So just keep in mind, keep that in mind as well. Okay, page 644 in your text there, page 644, we're talking about the strengths of acids and bases. Strengths of acids and bases. So what makes something a strong acid or a strong base? Is it its concentration only, or is it something else? Well, acids that completely ionize. Oh, and I have blanks here. Why do I have blanks here? I don't know. Okay. Are called what kind of acids? Help me out. What do you think would go in here? Strong is correct. Yes, strong acids. Okay, good. While acids that only partially ionize are called weak acids. Yeah, very good. Stronger acid solutions conduct electricity better. Stronger acid solutions conduct electricity better because ions carry electric charge. So if we have more ions in solution, these acids are completely ionizing, they will conduct electricity a bit better. So this is from your textbook here. Thought I'd just clip this into the notes for you. The light glows brightly when electrodes are placed in 0.1 molar hydrochloric acid solution, because all of the HCl is in the form of hydronium ions and chloride ions. And as you can see, the electricity is allowed to flow kind of in between the electrodes, and so it powers the light. We have a bit of a bit of an ion clock, I think, in the lab that I found the other day. I have no idea if it works. I haven't tried it. It looks pretty old, but it works under the same thing. So there's electric potential and things like that we'll talk about in later units. But basically, electricity is allowed to flow through solutions that are electrolytes that conduct electricity, because the ions carry the electrons along and they aren't inhibited that way. So yeah, so strong acid solutions conduct electricity. Think of car batteries, right? If you have your battery acid in there, if you have a strong solution like that, the electricity is allowed to flow, provides a bit of a buffer too for heat and different things. All right, weak acids only partially, because weak acids only partially ionize, there is a constant that indicates how soluble the acid is. Soluble, there is a blank for you. Now, I put soluble in quotes because it's kind of like the solubility product constant, equations and that concept that we just got finished learning about. But it's a little bit different. But this constant is just like the solubility constant, but it's called the acid ionization constant, or Ka. Okay, K sub A. That's what that is there. So we've had KEQ, the equilibrium constant. We've had KSP, the solubility product constant. And now we have Ka, the acid ionization constant. Okay? And they all kind of mean roughly the similar things. How soluble this is. Okay. All right. So we have a chart there. You have a chart in your notes. This is also maybe something like this is in the textbook. I'm not sure. But this indicates. I want to talk a little bit about this because just like solubility constants, the higher the value means more soluble it is. When you have a high Ka, a large Ka, that means it's a strong acid. So just take a look at this chart, and you have this in your notes as well. So hydroiodic acid, okay, so the acid is Hi, the base is I minus. The Ka, so the sort of the solubility or the ability for this to ionize or dissolve is much, much greater than 1. It is super high, okay, very strong acid. So we have much greater than 1 for hydroiodic, hydrobromic, hydrochloric acids. Nitric acid, sulfuric acids are pretty strong as well, not quite as strong as those binary ones. So they mostly ionize, pretty strong. Now we get into this grouping of acids here that would be considered, fairly starting to get weak. Anything less than 1 is starting to get a little bit weak. Still wouldn't go drinking sulfuric acid or anything like that. But if you look at acetic acid down here, okay, 1.76 times 10 to the negative 5. Now this is the acid that's in vinegar. It's only 5% of the vinegar that you would consume, so it's pretty small. So a 5%, plus this really small, fairly small Ka means that it's, a little bit on the weaker side, and so on. But these numbers will start to go, the factors of 10 will start to go down and down, and so we have very weak acids here. Obviously, water is a very small number, 1 times 10 to the negative 14. We're going to talk about that as well, but that would be pretty low. It's a very, very weak acid. So has anybody run across that the term for that's given to water because it can act like a base and an acid? Anybody run into that in the textbook, or since I asked last time? Okay. Starts with an A. Amphibious, close. Kind of comes from the same root. Okay, flip through. Water can act like an acid or a base, and we should be sort of around, 648, 649. It should be in your textbook there somewhere. Let me know if you find it. The term that... Page 639, amphoteric, A-M-P-H-O-T-E-R-I-C. I believe it's in the notes here somewhere, but we've talked about it a couple times here now, and so it's, amphoteric. So water can be both an acid and a base. Very, very weak acid, very, very weak base. Okay? Any questions about Ka? Now Kb is very similar, except we're talking about bases. So if you're talking about the strength of bases, a very strong base would have a very high Kb. And it would work the same way. Okay? All right. A strong base would have a very high Kb, very low Ka, if you want to think about it that way. Very, very low. Okay, based on the equilibrium constant that we've learned about before, the KEQ, the Ka is the ionization constant for an acid. This constant indicates how strong an acid is by giving a number value to the ability for an acid to release hydrogen ions. Okay, ionization constant tells you how strong an acid is by giving a number to the ability for the acid to release hydrogen ions. If the number is very high, it releases quite readily and completely. Very low, it's very reluctant to give up its hydrogen ions. Strong acids have Ka values that are extremely high because they completely ionize. If you think about solubility, the product of the ions in solution would be very high because it's mostly ions. You'll see for some, like in this above chart, hydroiodic acid, the Ka is just extremely high. So virtually all of the Ki compounds would split apart. There would be virtually no Ki compounds left in a solution of Hi, I meant. Okay, so the value is also useful, and it's when we're talking about calculations and things, just like KSP, the values are useful when we're talking about weak acids and how much they will contribute their hydrogen ions. So the Ka and Kb value is used similar to the KSP, as I mentioned. Let me make this a bit bigger for you. In determining concentrations of substances. When a weak acid or base ionizes in solution, the KSP tells how well something will dissolve. The Ka tells how well an acid dissolves, or the term we use specifically for acids would be ionizes, so produces those ions. Hopefully you're seeing the connection there between Ka and KSP, right? All right, this, I just thought this was neat. This is in your textbook as well, in your Glencoe text, but a deadly compound. Boy, you look at peaches or apricots here, you wouldn't think there's a deadly compound involved there, but what does it say? Hydrogen cyanide, HCN, is a poisonous gas that's found in the exhaust of vehicles, in tobacco, wood smoke, and in smoke from burning nitrogen-containing plastics. Some insects, such as millipedes and burnet moths, release hydrogen cyanide as a defense mechanism. A solution of hydrogen cyanide in water is called hydrocyanic acid. Okay, so cyanide ion is this right here. Okay, cyanide ion. So if you have HCN, this is the hydrocyanic acid here. Fruits that have pits, such as cherries or peaches, contain cyanohydrins, which convert to hydrocyanic acids in the digestive system if the pits are eaten. However, no hydrocyanic acid is produced in the flesh of these fruits, so the fruit can safely be eaten. So I don't know if you knew that. The reason, obviously, one of the reasons why you don't eat pits is because they're gross. They chip your teeth and they're hard to get down. But there's another good reason not to eat the pits of cherries and peaches and apricots and things like that, because they actually have compounds that when they get to your stomach, produce some nasty stuff. It's gonna make you sick. So if you have a pit in your stomach, you ever heard of that? You ever heard of that? A pit in your stomach? Ooh, just gave me a pit in my stomach. You kind of have this like really kind of like upset feeling in your stomach. A lot of times that expression is used for times when you're feeling uncomfortable about something, or you're anxious or worried about something. It's like a pit in your stomach. But I wonder where that came from. Probably came from here, didn't it? I don't know. If you eat a pit and you actually have it in your stomach, it starts to produce a poisonous gas, and well, I guess you eat enough pits, you might be done. But so what's the takeaway here? The Ka for hydrocyanic acid is 6.8 times 10 to the negative didn't come through, but that's a negative 10. So it is a weak acid, but it's still not good for you. So listen carefully, hear me out. A strong acid does not necessarily mean a deadly acid, where a weak acid would mean an acid that's okay to consume. That doesn't necessarily mean that. The strength of acids is how well, readily, and completely they ionize in solution. And the reason why you don't consume HCl or sulfuric acid is because it ionizes as soon as it hits the water in your mouth and blah, blah, blah. It just goes crazy. It's very acidic. It'll eat away at the lining of your throat and mouth and everything. And acid is good in your stomach, gastric acid, but not good going down, okay? That's why when you have like heartburn or stomach problems, that's basically your stomach acid is kind of like bubbling up and getting up into your tract there, and it's causing that burning heartburn sensation. That's actually acid coming up. You don't want acid. You want acid to stay in the stomach where it has all the protection and obviously it's made to be there. to dissolve your food and stuff like that. So it's nasty in there, but going down, not good. But weak acids can also be poisonous. Strong acids just dissociate violently. So there's one major note when determining concentrations with Ka or Kb. So just like solubility, guys, if you have something that's fairly insoluble, you can use the Ksp to determine sort of what the concentration of ions are. Well, remember, just as we talked in those days about low solubility and the presence of ions in compounds that have really low solubility, if you have an acid that's super weak, it's not going to produce many hydrogen ions in solution. And so if you have acids that are really weak, the difference between the original acid concentration and the final acid concentration is often next to nil. So with weak acids or bases that have Ka or Kb values of 10 to the negative 4 or less, the difference between the ions and the actual concentration can be ignored, similar to what we did with Ksp, right? So with Ksp, if the ion concentrations were severely low and we had common ion effect, if you have 0.2 moles of this ion coming in, and normally you would only have 0.000000002 moles naturally, well, then that difference is so big that can be ignored. So it's similar to what we did with Ksp there, but I'll maybe make that just note there. All right, so Glencoe text questions, page 649. You do have these also in your notes as well. So I'm going to get you to work on these. So 17 to 21 are listed right here. I want you, if you're in my class right now, please do those questions right now. I'll be available for help, and I'll give you the solutions to those a bit later in this video. So take a moment to try and answer these questions given what you've learned in this lesson here today. Okay, so here are the solutions on the screen here for questions 17 through 21, chapter 18. You can compare your answers with some of these on the screen.